Hello everyone, my name is Sungmin Lee, and today I'll be presenting our work, Spatial Discretization for Fine-Grained Zone Checks with SARCs. Many location-based services, such as geofencing or zone-based regulations, rely on a simple yet important question. Is the target object inside or outside a certain geographic zone? In the conventional setting, these zone checks are answered by a point-in polygon test. Given a target location and the polygon geometry of a zone, the PIP test directly evaluates the geometrical relationship between the point and the polygon. Recently, privacy has emerged as an important concern in designing such tests. Users may not want to reveal their precise location, while service providers and regulators still need to verify the zone membership result. Here, zero-knowledge proofs, especially scalable systems such as SARCs, become a promising framework. By definition, zero-knowledge proofs allows a prover to convince a third-party verifier that a test is passed without revealing the input to them. However, SARCs are designed to verify circuits with arithmetic operations over finite fields, while the PIP test has a lot of non-arithmetic operations such as comparison. Thus, a SARC-friendly alternative approach is needed for privacy-preserving location-based services. Many prior works addressed this issue by shifting runtime non-arithmetic operations to pre-processing and lookup table caching, at the cost of extra storage overhead. For instance, in zone checking, this can be done by discretizing the target spatial region into rectangular grid cells and storing pre-computed spatial information that can be directly used for zone membership tests. But this introduces a trade-off between the test precision and storage overhead as a grid resolution change. In practical zones with irregular boundaries or narrow regions, this trade-off becomes critical because small discretization errors can change the final membership results more easily. Moreover, the better design of spatial encoding can further improve this trade-off regime itself. However, these aspects have not yet been systematically studied for SARC-based zone checking. Therefore, in this work, we study grid resolution and spatial encoding design and propose a distance-aware discretization method for privacy-preserving zone checking. Given the short time limit, let me introduce the key design factor of our framework from a question. Which spatial information should be stored in the lookup table? A first naive answer to the question is center point Boolean encoding, which stores whether the center of each cell is inside the zone. It is the simplest and most direct representation of the membership, but it highly depends on a single center point. Another intuitive approach is voting-based Boolean encoding, which stores whether most of the cell area belongs to the zone or not. It can be less dependent on the single center point, but both Boolean-based approaches still cannot capture sub-cell level geometric information. To address this limited geometric fidelity of Boolean encodings, we instead propose the distance-aware encoding method. This method encodes continuous value boundary informations, specifically the sign distance values at grid vertices, and where the sign indicates zone membership and the magnitude captures boundary proximity. Given a query location, we interpolate these values using simple arithmetic operations to the nearest grid vertices, efficiently preserving the subcell geometry information. To evaluate our proposed method, we conducted a real-world evaluation on a 2x2 kilometer Beijing region covering up to 1,052 polygons. Now, I'd like to introduce one core evaluation result of our work. This figure compares how the three aforementioned encoding strategies behave as we use finer or coarser grains. As a higher curve in the figure means better zone check accuracy under the same grid resolution. As expected, All methods become more accurate as the grid becomes finer. However, more importantly, the main observation is that our distance-aware coding, depicted as the green line, outperforms the two naive Boolean encoding methods across grid resolutions, especially when the grid is very coarse. In conclusion, this work proposes a sign distance-based spatial encoding method for start-based zone checking. For more details and evaluations, please refer to our paper. Thank you for listening.